Okay, folks, let's knock out these homework problems very quickly here. Let's take the first one here. We've got f as a function from a to b. I've got a couple subsets of a. I want to prove that if c is a subset of d, then f of c is a subset of f of d. And then we'll talk about whether the converse holds or not. So the way we prove this is we say, all right, we're going to assume this. Let's take an element out of here. So let B, since this is all happening over here in B, let B be an element of f of c. Okay. Then there's got to be something over here in A. So I'll use A. This helps, A and B helps me keep track of what side of the function I'm on. So there's something over here in C such that f of this A gives me this B. Okay? Well, but what do I know about C? I know it's a subset of D. So then A is an element of D. Okay? But if A is in D, then that means that this B is in the image of D as well. Then B, right? Anytime I take something in D and plug it in and get something that's in the image of D, and that's my B. So we started with something in f of c, we showed it's in f of d. Oh, why did it do that? It was doing so well. I don't know why it changes out, but okay. I had much better resolution just a moment ago. I don't know. There, that's better. Stay there. Why does it change? I don't get it. So anyway, what we've shown is then that f of c is a subset of f of d. So we've proven that. Now the question is about the converse. Let's state the converse. If f of c is a subset of f of d, then c is a subset of d. The question is, does that hold? I don't think so. Let me give you hold. No. So here is a counter example. Let's let A and B be the same set, just 1 and 2. And I'll let C, which has to be a subset of that, just be the whole thing. Why does it do that? That's really weird. Okay. Be the whole thing, and then I'll let D be just the one thing. So I'm setting this up so that here that C is not a subset of D. Okay. And I'm just going to map things accordingly. Let f of x be 1 for both 1 and 2. So let me draw the picture. Here's A with 1 and 2. Here's B with 1 and 2. And everything is mapping to 1. Okay? Then f of c, well, c is the whole thing. So I just get 1 and that's it. And then f of d, well, d is just 1, which goes to 1. So I do get f of c as a subset of f of d, which is what I wanted. But you can tell here c is not a subset of d. So the converse will not hold. Okay? Alright. First one out of the way. Problem 10 here says, okay, you got a function A to B, C and D are subsets of A. Prove that F of the union of two sets in A is the union of their images. Okay, F of C and F of D. So again, proof sets are equal. We do the double set inclusion, right? And these images are over in B somewhere, so I'm going to say let B be an element of F of C union D. Okay, now what that means is there's something over in A, really something over there in C union D, that gives me that B. So then there exists an A inside of C union D such that F of that A gives me the B. Okay? Well, then either A is in C or A is in D. So I got to look at the two cases. If A is in C, then that means that B is in the image of C. And that means B would be in the image of C union with anything, but in particular F of D. Okay. If A is in D, then that means this B that I'm talking about has to be in the image of D. And that means it'd be in the union of F of D with anything, but in particular F of C. So what we've shown here is that starting with something over here, it ends up over there. So F of C union D is a subset then of F of C union F of D. So now we want to go the other way. Now let B be an element of F of C union F of D. Then B is in one or the other. So you got to look at the two cases. If B is in F of C, then there exists something over here in C such that F of A gives me that B. Okay? But this A being in C, well, then A is in C union anything, but in particular D, which means this B then is also in the image of C union D. If this B is in F of D, the image of D, then there has to be something. I can reuse A because I'm done with that part now. This A is in D such that F of A is B. But if it's in D, it's certainly in D union anything, particularly C. Then B is in the image of C union D. So no matter how you slice it, starting with something here, it ends up there. Thus, F of C union F of D is a subset of F of C union D. So you got set inclusion both ways. Last sentence, therefore, F of C union D is equal to F of C union F of D. Okay, which is what we had to show. Okay. Oops. Third problem, and I think there's a part I forgot to write down here. We want to prove that F of C is minus F of D is a subset of F of C minus D. God, yeah, we should stop doing that. But then there's also this part. Also show that they're equal. If and only if f is 1, 2, 1. Okay, so there's actually three kind of separate things we're going to have to do in this proof. We'll start with the first part here. Let's take something B in f of C minus f of D. Now what that means is then B is in f of C, but B is not an element of f of D. So since it's here, there's got to be something in C that gets me B. There exists an A in C such that f of A equals this B. Okay? This A cannot be in D, though. So I'll just say note that. A not in D, since if it was, then B would also be in f of D. Okay, and that would give us a contradiction. So A is in C, but not in D. Then A is in C minus D. And that means that this B is in the image of C minus D. And so I started with something there, showed it's here. Thus, f of C minus f of D is a subset of f of C minus D. Now, to show the rest of this, we could completely start over and assume this and prove that, and assume this and prove that. We've got part of that for free. I think what I'd like to do, just to minimize my steps, is say, okay, now let's say it's 1 to 1, and see if we can get the other direction, right? One to one, and let's let B be something on this side. Okay? Now there'll come a point in this side of the proof where it's going to become pretty crucial, actually, that f be 1 to 1. But let's wait till we get there. What this means then is then there exists some A in C minus D such that f of A gives me the B. Okay? This means then that A is in C, but A is not in D. Okay? Well, that means then that B is in the image of C. Okay? Now we've got to consider, is it in the image of D? Now, see, in typical things, just because I've got f of A going to B, there can be other things that are sending me to B, this letter B, right? So let's think about this just a second. Okay, so suppose B is in f of D. Okay? Then there would exist something in D such that f of x, now see, it doesn't have to be A in general, right? It could be anything. Such that f of x gives me the B. But here I've got then f of A equal to f of x. Since f is 1 to 1, this x, though, has to be A. And that means that A is in D. And that's a contradiction. A is not in D. Thus, B is not in f of C. That was our assumption. D. I'm sorry. B is not in f of D, excuse me. That was our assumption. And B is then in f of C minus f of D. Okay. Which we started with it here, got there. Thus, and I'll write over here, f of C minus D is a subset of f of C minus f of D in this case, where f is 1 to 1, and so that shows that they're equal. Is 1 to 1. Okay? But now what we got to do is we got to say, all right, let's assume that f of C minus D is equal to f of C minus f of D for our f. And then how do we show things are 1 to 1? Well, okay. Suppose that we have A1 and A2 in A such that f of A1 equals f of A2. Okay? And what we have to do is show that A1 and A2 are equal. I don't know what that was all about. I just lost my screen. Okay, sorry. Okay. But here's the thing. Let's suppose they're distinct. If I do that, I can put 1 in the set C, and I can put 1 in the set D. Okay? Then, what have I got? Well, I've got f of C minus D. C minus D is just A1, right? Which just gets me f of A1. This is the set with just f of A1 in it. Okay? And then f of C is f of A1 and f of D is f of A2, which is equal to A1, then f of C minus f of D, they're the same. So I have to, let's see that. They're the same, and so this is an empty set. But it has to be this. That was our assumption. A contradiction. Thus, A1 and A2 are the same thing. Okay? So that got us through 11. Now let's take a look at 12. And 12, we fumbled around with the converse on it, but there's it just took me a while to think about it, but there's a good counterexample actually to the converse. Okay, so we've got f and b. F is a function from a to b. We've got C and D are subsets now of B. Okay, we want to prove that if C is a subset of D, then F inverse of C is a subset of F inverse of D. Okay, and then we'll ask the question, does that hold? All right, so let's look at this. Let's say we start with something here, and this is over in the set A. So I'll use a lowercase a. Let A be in F inverse of C. Now what that means is, and we could assign it a letter if we want to, but that means that there's something over here in the set C that A maps to. F of A would give me something here. I'm just going to call it F of A. Could call it B, but I mean, let's save the letterage. We don't need it, right? So F of A then is in C. But C is a subset of D, so F of A is an element of D, which means there's a thing here in D that gets mapped back to A, which means that this A is in the inverse image of D. Okay? Thus, you've got that F inverse of C is a subset of F inverse of D. Now, the converse of this would be, okay, the converse of this would say if the inverse of C is a subset of the inverse of D, then C is a subset of D. Not true. Not true. Holds. No. Here's a counterexample. And I'll talk it and I'll draw it too. So let A and B be 1, 2, and 3. I'll let C be 1 and 2. And I'll let D be 2 and 3. Now the thing I'm going to point out to you is that C is not a subset of D, so I just need to do my function accordingly. Let f of x be 2. For x equals 1, 2, and 3. So if I draw this, here's A, 1, 2, 3. Here's B, 1, 2, 3. Here's C. Here's D. But I'm mapping everything to 2. Okay? So let's look at what we got. F inverse of C. Well, the only thing that gets mapped back is 2, and it gets mapped back all the way to A, right? F inverse of D, well, the only thing there that gets mapped back is the 2, and it goes to everything. So F inverse of C is a subset of F inverse of D, but C is not a subset of D. Okay. All right. So that is that one. Okay. 13 says, okay, we've got a function a to b. We've got two sets C and D that are subsets of B. And I want to prove that F inverse of C intersect D is the same as F inverse of C intersect F inverse of D. Okay? So we're going to prove the two sets are equal. We do that with double set inclusion. Let's let A be something here in F inverse of C intersect D. Then that means that there's something in C intersect D that A gets mapped to. I'm just going to call it F of A. Is in C intersect D. But that means then that F of A is in D and C. I'm sorry, I wrote D first. I don't know why. Okay. Then that means that A is in the inverse image of C. I'll do it right this time. C. And A is in the inverse image of D. Thus, A is in both F inverse of C and F inverse of D, puts it in the intersection. So we started here, finished there. Thus, F inverse of C intersect D is a subset of F inverse of C intersect F inverse of D. Now let's go the other way. Now let A be an element of F inverse of C intersect F inverse of D. Then it's in both. Okay. Well, then that tells us there's something in C that A maps to. I'm just going to call it F of A. Okay. It's going to be in C. That's what this means. And there's something in D that A gets mapped to. It's got to be the same thing. F is a function, so whatever F of A is, it's the same thing. So I'm just going to call it F of A. And F of A also is in D. That means that F of A is in the union of those two, right? Not union, intersection, sorry. Intersection of those two. Thus, A is in the inverse image of C intersect D. So we start with something here, proved it's there. Thus, F inverse C intersect F inverse D is a subset of F inverse C intersect D. We have double set inclusion, so therefore the sets are equal. Okay, which is what we're trying to show. Okay, one last problem to work here, and that is that we've got a function from A to B, C and D subsets of B. We want to show that the inverse image of C minus D is the inverse image of C minus the inverse image of D. Okay, so showing sets are equal, pretty common thing. Let this is going to be, inverse images are in the domain, so I'm going to let my variable be, my element be A. Let A be an element of F inverse of C minus D. Okay, and what that means is then there's something in C minus D that A gets mapped to. I'm just going to call it f of A. Then f of A is in C, but f of A is not an element of D. Okay. Well, then it's pretty clear that A is in the inverse image of C. And then what we're saying is that since A does not get mapped to D, there's no way to get back to it. There's no, let me do it the correct way. Here's my A, here's my B. If A got mapped to D, then there'd be a way back. If it doesn't get mapped to D, it's not an inverse image. So A is not going to be in F inverse D. That means then that A is in F inverse C, but not D. So it's in that minus that. We started here, we ended up there. Thus, I already said that. Thus, F inverse of C minus D is a subset of F inverse of C minus F inverse of D. Okay? Now, let A be an element of F inverse of C minus F inverse of D. Then, I typically say then. Then, A is an element of F inverse of C, but A is not an element of the inverse of D, F inverse of D. So this means there's something in C that A gets mapped to. I'm just going to call it F of A. Okay. But since I can't get to A by taking the inverse image of things in D, F of A doesn't get mapped to D. Thus, F of A is in C minus D. Then that means that, wow, my resolution's really sorry on this. I'm sorry. I don't know what's going on. Something wrong with my internet or what's happening? I'm really not sure. But anyway, then this means that A is in the inverse image of C minus D. So I started with something here, showed it was something there. Thus, I've got F inverse of C minus F inverse of D is a subset of F inverse C minus D. Boy, that's horrible. I wonder if my internet, it could have something to do with, I'm using Skype, and so Skype uses what internet, it sets the resolution according to the amount of internet flow through you've got. And so, that's really weird. Okay. It's pretty sorry. Oh, much better. Well, it's not great, but still it's better. So, you got this subset of this subset of that. Therefore, the sets are equal. And we're done. Okay? So, hope that helps with the homework. And be thinking about that test. And if you have questions, ask me, and I will talk to you later.